Welcome, everybody. It's my pleasure today to introduce Majhi, who will be telling us about demystifying Latschevs Theorem.
Thanks, Henry, for the introduction. Good morning, everyone. Thanks for joining today. My name is Sush. I did my PhD from Tulane University. Then I joined UC Berkeley as a postdoc. I was there for 2 years. Now, currently, I am in the data science program with George Washington University. Today, we'll talk about Latschevs Theorem and how we can improve Latschevs Theorem and use the theorem for shape reconstruction. All right. Okay. So here's the agenda for today. First, we'll present the problem of shape reconstruction, especially manifold reconstruction. And then we'll talk about Vietoris complexes, just the basic definition of Vietoris complexes. And then we'll bring up the theorems of Hausmann and then Latshev. And then finally, we'll try to demystify Latschevs theorem a bit, especially using Young's theorem on manifolds. This is something that could be of general interest. And then if we have time, we can go over the sketch of the proof. Finally, we'll take questions. All right, let's begin. The problem of shape reconstruction is a challenging problem. A shape is usually modeled as a metric space, M. We can take a compact metric space, but let's not make any assumptions right now. Compact space can be a very general set, right? But one can also talk about very special cases, for example, reconstruction of metric graphs. Or for today, let's talk about reconstruction of Riemannian manifolds. So we're taking M to be a Riemannian manifold with its geometry along with the topology. Now, sample, we're going to reconstruct M, pretending that M is hidden, but what we have a finite sample, again a metric space, X, very close to M. We'll define what closeness can mean in different contexts, but one commonly used error model is Hausdorff proximity. This is when you have your Riemannian manifold M being a submanifold nicely embedded in the Euclidean space, and the sample X is also let's pretend it's a finite or a compact subset of the Euclidean space, and they're nicely embedded very close to each other in the sense of Hausdorff. So the Hausdorff distance between M and X being very close. But for today, we'll talk about a different type of error scheme where we're assuming that M, the manifold to reconstruct, and the space X, the sample, they're abstract metric spaces without any possible embedding. Maybe even if they have any embedding, we'll try to disregard them. And we're asking if, for a good sample, we're asking if they have a very small Gromov-Hausdorff distance. I'll give you the definition shortly, but roughly it means that they're metrically very close. Our goal would be to infer the topology of this hidden manifold M just from the sample X. By inferring the topology, one can possibly ask for the calculation of the Betti numbers. For example, how many connected components in 0 dimension, or in 1 dimension, how many cycles M has, or in higher dimension, how many voids, and so on. You can keep going, but this would give you just the topological features, not the exact topology of them. But if that's what we're interested in, one can definitely do so. But today we're feeling a little more ambitious. We're going to reconstruct not only the homology or homotopy groups, but also the topology of M. We're asking for a topological reconstruction. We're saying if any way we can use the sample X to construct a topological space, we can call it M tilde. It's going to be a reconstruction of M, so that M tilde and M, the manifold, have the same homotopy type. In other words, there's a homotopy equivalence map going from M tilde to M, so on. So for today, we'll reconstruct Riemannian manifolds. We're also assuming that we have closed Riemannian manifold. It doesn't have any boundary. Also, it's compact. So it's a nice Riemannian manifold. And the sample being an abstract, again, matrix space, it's very close in the Gromov-Hausdorff distance to M. And our reconstruction goal here is to construct a topological space, M tilde, which is going to be a Vietoris complex today. We'll talk about Vietoris complexes, but the idea is to construct such a space that has the same homotopy type of M. So you retain not only the topological features, the homology, the homotopy, and so on, but also homotopy equivalence. All right. So that's our agenda for today. Let's move on. I'm sure the audience is quite familiar with Vietoris complexes, but still I'll try to give a very basic working definition, at least very quickly. To construct Vietoris complexes, what we need is a matrix space, X, in this case, our sample. We take the sample and then build a Vietoris complex on top of it to call it our reconstructed space, M tilde, right? So we take a matrix space. We also need a scale, so beta, positive scale. And then what we're going to build is an abstract simplicial complex, call it R, sometimes called VR for Vietoris strips. The scale beta is in the subscript, and the set X, or the matrix space X, is inside it. So this Vietoris complex is going to be an abstract simplicial complex, combinatorial complex, so that for each subset, finite subset A from X, if the diameter of the set, the soup of all possible pairwise distances, that's the diameter. If the diameter is at most, sorry, there's a typo, it's going to be beta. If it's at most beta, then we throw a simplex in our Vietoris complex of dimension k-1. So that's the rough idea. This is how we build the Vietoris complex. I have a little demo here. So we can take a finite set of points. So this is our X. Let's pretend this is our X. And on the left, I can choose my scale. Right now it's 0. So only the singletons, the vertex set, is all what we have in the Vietoris complex. But if we keep growing this scale, you will see that more and more points would get connected. For example, when I am at this point, and keep going. All right, so these 2 points right now for this beta, these 2 points, and this is our subset A. Right now, this subset has its diameter at most beta, so we connect them by an edge or one simplex. And if you keep going, more and more points are now getting connected by edges, but also at this point, see, not only we're getting a new edge, but also the triangle is filled in because these 3 points now, 3-point combination, A as its diameter at most the chosen beta. And if you keep going at some point, everything would be connected, possibly more polyhedra and so on. I'm not showing the three-dimensional things here. It's just the shadow of the actual Vietoris complex, but I think you got the idea. All right, so with this definition of Vietoris complex, what we're going to do, we'll take our sample. We're pretending today that it's a finite sample, finite space, so it doesn't have interesting topology. It's just discrete topology on top of it. But we're going to create Vietoris complexes on top of it. So the geometry realization of the Vietoris complex would give us a nice topological space with interesting topology, and hopefully the topology would be what we want for M, the actual underlying Hebrew manifold. Okay, let's move on. All right, now I'm ready to state Hausmann's theorem, but I need a little definition here. it's called conjecture radius. Usually what happens if you have a manifold, let's pretend on the right we have a manifold. It's the circle of circumference 1. It's a unit circumference circle. You take a point, you take any point, let's take the North Pole, as you can see, the black dot on the top. And if you keep growing a metric ball of certain radius, let's say my radius is 0.1, right? If your radius is very small, the metric balls are geodesically convex. By geodesically convex, I mean if you take any 2 points from the metric ball, there's a unique shortest path going through the space. And it happens as long as you have a very small radius for any point you choose on a manifold. But things will change if you keep growing the radius of the ball. And now I still probably have a geodesic metric ball. You can still, if you take 2 points and try to connect them, you'll find a unique geodesic passing through the circle pretty much within the green arc. But when you are, again, this is an open ball, right? For a quarter of the circumference, I still have, this is an open ball, I still have a convex metric ball. But as soon as I go beyond a quarter, as you can see, the antipodals are now included in the metric ball, and you can go either this way or the other way to join them by a shortest geodesic. But now it's not convex, right? So, all right, so let's see. So rough definition of contextual radius is you take a Riemannian manifold. It doesn't have to be a Riemannian manifold as long as you have a length space where you can talk about lengths and geodesics and so on. You can define its convective radius to be the largest such radius that would work for all points on the manifold, so that you have a geodesic metric ball. So the metric balls are convex. And largest such radius would be called the contextual radius. For the circle, as we have just demonstrated, it's a quarter of the circumference. We'll denote today the contextual radius by a rho of m. One can also easily, well, with some calculation, can see that if you have a compact manifold, the contextual radius is a positive number. Now, contextual radius is going to show up in Hausmann's theorem. Hausmann's theorem, although it doesn't really help directly, although any finite reconstruction, but it will implicitly help us. And also, it's very easy to state. So here is Hausmann's theorem. It says that if your scale for Vietoris complex, beta, is within the convexity radius of the manifold, then the Vietoris complex that you build on the entire manifold with the scale beta is going to be homotopy equivalent to M. And Hausmann, in his paper, actually constructed explicitly a map, the homotopy equivalence map in this paper. All right, so that's Hausmann's theorem, and today we're going to talk about use Hausmann's theorem to demystify Latschevs theorem. Any questions so far? All right, let's move on. Well, a few comments on Hausmann's theorem as I have them here. If you've noticed, the Vietoris complex has the entire manifold as its vertex set. So the vertex set is possibly uncountable, and it's not a very nice Vietoris complex that we can manipulate, right? But the question that Hausmann poses, and this question is going to be very critical in our shape reconstruction, is what happens if you take a finite dense subset from the manifold and you build the same Vietoris complex, maybe within some contextual radius, rho of M, and so on, would it still capture the homotopic type of M? This is an intriguing question. And this question was taken up later by Latschev to show that this is what would actually happen as long as you have control over all the parameters that you have, beta, contextual areas, and so on. Also, how dense the subset should be in M, and so on. But we can also generalize Hausmann's question to say this. So more generally, can we also ask what happens if we have an abstract sample, not necessarily a subset of M, but a general metric space with a small Gromov-Hausdorff distance, which we'll define shortly, with a very small Gromov-Hausdorff distance. In a way, they are metrically very close. So that's a way of saying that you have a dense sample of M. Can we, similar to Hausmann, can we do a Vietoris complex on the sample and still have capture the topology of M? The question was answered by Latshev later. We'll talk about it, but first the definition of Gromov-Hausdorff distance here. Gromov-Hausdorff distance is a distance measure defined between two abstract matrix spaces. They don't need to be embedded in a common ambient, but what the definition does, the definition tries to embed the two spaces. Let's say we have two matrix spaces, abstract X and Y, as you can see on the right in the picture. The definition tries to embed them isometrically in a yet another metric space, it's called Z, and then takes the Hausdorff distance in that ambient and tries out different isometries and different ambient spaces, Z, as long as to get the best such embedding, right? So the definition is here, although the first glance it could be quite difficult to parse, but this is what is happening. If you take a look at the picture on the right, you have two matrix spaces, X and Y. We try to embed them into a third matrix space, Z, via isometries F and G, so that you want distorting pointwise distances. Once embedded, you can talk about Hausdorff distance inside of Z. And then you try out all different isometries and all different ambients as long so that you have the best one. The best one is going to give you the Gromov-Hausdorff distance. So in a way, you are trying to give a distance measure that reveals disparity if X and Y are very different metrically. All right, now using this error scheme in terms of Gromov-Hausdorff distance, we can now talk about Latschevs theorem. Latschevs theorem tells us that, well, it's answering Hausmann's original question, but qualitatively. So it says if you have a closed Riemannian manifold M, then it's possible to find a positive number, epsilon naught. Latshev doesn't say how to come up with the number, but qualitatively one can construct, or it's possible to construct such a number, a bound for the scale of the Vietoris complex, so that if you take your beta scale for the Vietoris complex within epsilon 0, then you can get another number, delta, which would control the density of your sample, which would control the Gromov-Hausdorff distance between M, the manifold, and the space, the sample S, X. So as long as your Gromov-Hausdorff distance is smaller than delta, the tolerance for the density, then the Vietoris complex at the scale beta on the sample would give you the right homotopy type for M. A few comments on this. This is a remarkable theorem, and I consider this as a stepping stone to finite reconstruction of Riemannian manifolds. But there's something quite impractical about this theorem. This is only qualitative. It talks about the epsilon naught to exist for any closed Riemannian manifold, but it doesn't say how you're going to choose such a number. Of course, the geometry would play a role. geometry of M, and using the geometry of M, you can possibly try to come up with such a threshold epsilon 0, and that's the motto of today's talk. So there has been a recent development. Well, there have been two recent developments last year, also this year, where such a result, like Latschevs theorem, has been tried to, I would say, was restated, but in a more quantitative way. We'll take a look at that. Any questions so far? All right, very nice. So we have Latschevs theorem here. Let's move on. The takeaway from here is if you have a closed Riemannian manifold and a finite sample, they're very close in Hausdorff distance, it's possible, again, qualitatively, to find a bound on the scale parameter that you are going to choose, the beta, so that if you grow your Vietoris complex on the sample up to beta, you still have the same homotopy type as M. So you can topologically reconstruct M. All right. Moving on, last year, there was a development, and metric graphs have been reconstructed using the same Latschevs type theorem. And here is a statement: if you have a compact path-connected metric space, these assumptions, but if you have a metric graph that you are trying to reconstruct, and again, it's a length space, it's a nice length space, so we can define convectory radius also for graphs, then one can use this bound, as you can see here. Rho is the convectory radius. Again, if you have a graph, the convectory radius would be a quarter of the shortest, or the shortest cycle, simple cycle of the graph, right? The same way we did it for the circle. But as long as you are within this bound and you have a strong Gromov-Hausdorff condition on the left, then for such a beta, such a scale, the Vietoris complex on the sample gives you the right homotopy type of the graph. Again, metric graphs are very special cases of Riemannian, well, of length spaces where you can talk about convectory radius. Manifolds would be a different story because graphs are not manifolds. They have branchings, they have corners, and so on. But for manifolds, one can wonder what would happen to such a reconstruction scheme. If we're trying to follow Latschevs theorem and trying to give such a quantitative result for manifolds, it's going to be hard. But as it turns out, this year, again, you will have to take into account the geometry of the manifold. Let's say we have a Riemannian manifold, M. We're assuming that it's closed without boundary. Compact, it's also connected, and you have a compact metric space X, we call it our sample. And as long as you have control over your scale, beta, and this relationship basically controlling everything. On the right, we have rho of M, the contextual radius. Also, we see this little kappa. This little kappa comes out of the geometry of the manifold. Basically, for a Riemannian manifold, we can abstractly define curvature. But also, using the abstract notion of curvature, one can talk about sectional curvatures. It's basically the usual Gaussian curvature for surfaces, but a little more general, so that we can incorporate high dimensional manifold. As long as you have control over the upper bound of your sectional curvature of the manifold at different points, also for different sections, then one can control the scale parameter beta in this way, so that the Vietoris complex built on top of the sample would give you the homotopy equivalence, give you a homotopy equivalence. So that is the topology of M. Any questions so far? All right, we'll try to go over the sketch of the proof in a while. But this is a general scheme. We need to take into account not only the topology of the manifold, as Latschev did, but also the geometry of the manifold played its role in such a scheme. But here is the quantitative version of Latschevs theorem, where we can reconstruct a closed connector Riemannian manifold from a finite sample as long as the Gromov-Hausdorff distance between them is very small, and also you have control over the upper bound of the sectional curvatures of the manifold at different points. Okay, moving on. Yeah, I have described what kappa means here. So basically, the idea of the proof uses barycentric subdivision. It's quite common in topology to use barycentric subdivision. We won't go into the details of barycentric subdivision, but also the proof uses Young's theorem as a crucial ingredient. We'll talk about Young's theorem because I thought it could be of general interest, because Young's theorem applies usually for sets in Euclidean space, but also one can generalize them subsets on manifolds. So let's talk a bit about Young's theorem. The classical Young's theorem is for Euclidean spaces. It says that if you have a compact subset A of the Euclidean space Rn, then what happens? There exists a unique circumcenter. So basically, you can kind of cover, as you can see on the right, the purple, I think it's pink, triangle is our set A. You can also consider the extreme points, the vertices. So that's our set A. One can have a circumcenter, a unique circumcenter, the point in the middle, that's our circumcenter, so that you can cover the entire triangle with the smallest radius around circumcenter. So basically, we're talking about a circumball, the smallest ball, so that you can enclose the entire set A. And the center of the ball is called the circumcenter, and the smallest such radius to enclose the entire set will be called the circumradius, as denoted here by R of A. But also, Young's theorem states that if you have control over the diameter, if you know the diameter of the set A, for example, for this purple, for this pink triangle, the diameter of the triangle is the longest side, right? So if you happen to know the longest side, then you can also get, you can control the circumradius. The circumradius is going to be a number strictly smaller than the diameter. But also, here's the exact calculation. At most, it can be square root n, the dimension of the space you are in, divided by 2 times n plus 1. So it says that if you have a compact set, then you can enclose it by the smallest enclosing ball with a unique circumcenter. And the circumradius is going to be strictly smaller than the diameter of the set. But this theorem can also be extended to sets on manifolds. As it turns out, there's a result from Dexter, 1997. Dexter first extended the results of Young's to constant curvature spaces, positive hyperbolic spaces, but negative curvature hyperbolic spaces, also positively curved spaces like the circle, not the circle, but torus. Not the torus, it has both, but the idea is that if you happen to know the sectional curvature, or happen to have the bound on the sectional curvature, if you have a hyperbolic space of negative curvature at all points, sectional curvature, then you can have this relationship, the first line. But if k is 0, as in the flat case for circles, for flat tori, also for Euclidean spaces and so on, you can go back to the classical Young's theorem. As you can see, on the right, we have the circumradius, and it's strictly smaller than the diameter of the space, the diameter of A, as we saw in the classical case. But also, if you happen to have at least one point on the manifold with positive sectional curvature, then it gets tricky, but you can still control the circumradius of a compact set, as long as the compact set is lying within a very small neighborhood where things are convex, the way we see things in the Euclidean space. So this happened to be the main ingredient for our extension of Latschevs theorem. But the takeaway here is if you have a compact subset of a Riemannian manifold with controlled diameter, it's controlled by a relation, the contextual radius, also the curvature, sectional curvature, and so on, then you can also control the circumradius. Also, to mention here, we note that the circumcenter in this case may not be a unique point, but still you can have a unique circumradius where the circumradius is strictly smaller than the diameter of the set. All right, moving on. Now, since we have time, let's go over the sketch of the proof. So basically what happens, let me start my tablet. Right. So here X is the sample and M is the manifold. And what happens, since we have control over the Hausdorff distance, we can have this simplicial chain. Basically, these numbers, let me get them right. All right. So this is coming from the fact that we have a very small controlled Hausdorff distance. So small Hausdorff distance can give you such a simplicial chain. The first match, so the idea is that if the Hausdorff distance is controlled, then you can have a correspondence with controlled distortion. And the correspondence would set up a map on the vertices like M and M to X, but then eventually, if you extend them to simplicial maps, you would get these two simplicial maps. The idea is that this map phi here, I'll write here, I'm going to show that phi induces, well, phi, or maybe next step. So the first map phi would give us the homotopy equivalence. So that's our goal. We want to show that the first map is homotopy equivalence so that what happens, note here that we can control these things as long as this is smaller than the contextual radius. We can invoke Hausmann's theorem, and Hausmann will tell us that this object here is homotopy equivalent to the manifold because this is our Rips complex on the entire manifold. Also, this is homotopy equivalent to the manifold, right? But also, you can show that the composition of these two simplicial maps, P and C, is contiguous to the inclusion. So there's a natural inclusion from the small scale Vietoris complex to a larger scale Vietoris complex. So the idea is that the composition, I'll use a different color here. So the idea is that we want to set up a homotopy equivalence, and we're going to invoke Whitehead's theorem and show that phi induces isomorphisms on homotopy groups. For all k. So if you take any dimension k, then you want to show that phi would induce an isomorphism between the homotopy groups of these two spaces. Let's take a fixed dimension k. We can kind of readily see that phi would induce an injective isomorphism because from Haussmann, this is an isomorphism. This would induce an isomorphism. This is inclusion, right? And the first map has to be an injection. So this is kind of available to us. The only thing that we need to show that the induced map is also surjective. And this is quite difficult to show. The technique that we used is, let me erase some part of it. Let's erase this from here. The idea was that if we take a simplex from here, let's pretend that we have the geometric realization of the space. So it's the convex hull of this entire thing. Then correspondingly, I'm using yellow color to show that you have a corresponding geodesic triangle on the manifold. So on the manifold, what happens for these 3 points, you have a corresponding geodesic triangle on the manifold. So this is happening on the manifold, and this is happening here. Okay. Now, by Young's theorem, if you can control the diameter of this geodesic triangle, what happens, there would exist at least one circumcenter somewhere, we don't know where. Let's pretend that it's here. That's our circumcenter. Also, each side would have its own circumcenter, right? Some other name, maybe prime here and so on. And also you can control the circumradius, and circumradius would have a constant factor of the diameter of the original geodesic triangle. So in a way, if you drew these geodesic triangles inside it, so basically you're subdividing, see? So that's the first simplicial subdivision of the geodesic triangle. Then each triangle here would have a diameter strictly smaller than the actual diameter of the geodesic triangle. And you can control those parameters nicely. You have to do some juggling with the parameters. And what happens, there would be a corresponding simplicial subdivision here, so that each triangle would be a corresponding simplex here. So if you are taking, let's pretend that we are doing it for homology, although for homotopy, we need homotopy for Whitehead's theorem, but if you're doing it for homology, you would take a K-chain, let's take a triangle, right? And then correspondingly, you can divide that K-chain, or a simplex basically in this case, to get a homologous K-chain in here. And that would show that phi star would induce a surjective homomorphism between these two spaces. So you take a simplex, subdivide, then use Young's theorem so that each subdivided triangle would correspond to something here, then so that everything matches, so that you have a homologous setup, and it's basically the same cycle. And
I see. So you're looking at these Baryshnik subdivisions because to show surjectivity of phi on homotopy, you need to reduce the scale, and you do that by sort of subdividing because you have a buried center in the manifold.
Right. So this is basically from Young's theorem. Any more questions? I think we can take a few questions at this point.
Another question. So x naught, x1, etc. Those are points in X. But then when you drew this geodesic triangle in M, that's using the vertices are points that were correspondent to x0, x1, and x2, right? Okay.
Right. Yes. Since we have a correspondence from this Gromov-Hausdorff distance with controlled distortion, we can use that to create a corresponding triangle, a geodesic triangle of the manifold. That's the idea. If there are no more questions, and then what follows from here, it would be using Whitehead's theorem to show that phi is in fact a homotopy equivalence. So using Hausmann's theorem to implicitly, Whitehead's theorem to implicitly show that phi is a homotopy equivalence. All right, let's move on. Let me reconnect, or maybe refresh. All right. Now move on. Okay, now a few points here. For abstract setup, abstract manifold and sample abstract, we can quantitatively prove the theorem. But also, if you have a Euclidean submanifold, where your sample is also a Euclidean subset with a small Hausdorff distance, this has also been shown that this can be done because using just the reach of the submanifold, because the reach of the submanifold can control both the sectional curvatures, also the contextual areas. So the same technique of subdividing and using Jung's theorem can also be applied to get a reconstruction scheme for Euclidean submanifolds. So that's about topological reconstruction using homotopy equivalences. But what happens to geometric reconstruction? Let's say I have a Euclidean submanifold and a sample. The Vietoris complex is only good to get the topology of the submanifold, the hidden space. But if we want to also reconstruct the ground truth geometrically, then the Vietoris complex, well, may not be very helpful because these are complexes, well, combinatorial complexes living in very high dimensional spaces, right? One possibility is we project them into the same ambient where the submanifold is and look at the shadow of each simplex. The shadow came up in Eric Chambers and others' papers a long time ago, but these are very delicate. The topology of shadows is very delicate. And I don't know whether projecting the Vietoris complexes, although the actual Vietoris complexes have the same homotopy type, after projecting them or taking their shadow into the same ambient, I'm not sure whether it would retain the same topology or not, but that's something to explore further. Also, one can definitely consider spaces beyond manifolds, because Jung's theorem has been also extended for cat case spaces, like length spaces that you have controlled curvature in the sense of Alexandrov can define curvature in some way. It's not very straightforward, but one can have Jung's theorem, a version of it, for cat case spaces. One can try to also look into this type of reconstruction of length spaces using Jung's theorem for cat case spaces. Also, for Euclidean subspaces, what if we have something beyond manifolds, let's say a simplicial complex, maybe a triangulation of a space embedded into RD. And we have a finite sample around it in the sense of Hausdorff, say, can we use these techniques to extend the reconstruction schemes that we have currently for submanifolds? I've been collaborating with Rafal Komandarczyk from Tulane University with his students, graduate students, to look into this further. All right, that's all I had. And these are the references. I'm going to also put my email in the chat. If you find these materials remotely interesting, please reach out to me. We can talk further. We can also try to think together on some of these problems. Thank you very much.
Thanks so much. Thank you, Sush. So before we get to questions, why don't we briefly unmute ourselves and applaud for the speaker. All right. Questions for Sush?
Questions?
Let me ask one question, Sush. So, I mean, certainly historically, Hausmann's paper played a big role for Latschev's paper, because Hausmann asked this question, should this be possible? And Latshev studied this. Now, in your proof, which I quite like, you use Hausmann's theorem, right? Because you have the manifold on either side and the sample in the middle. Do you remember in Latschev's proof, does he sort of use Hausmann's theorem along the way?
He actually doesn't. He does everything on flat manifolds. And then at the end, although honestly, I didn't fully understand Latschev's arguments, but the idea was to use Hausmann's theorem. Maybe I'm wrong.
I'm not positive on this point either. I'm not sure. Yeah.
But it'd be a nice reading exercise to understand Latschev's theorem. Also, at some point, I think Zieger mentioned that there is something wrong with Latschev's argument. I think some constants are off.
Right, but also he knows how to fix it. Change.
Right. It can be fixed, definitely. Mm-hmm.
Yeah. I think so. From what I've heard, maybe there's something related to convexity versus star convexity. There too. But I really like how the sort of the perspective of interleavings from persistence is appearing directly into your proof, right? Because Latschev's theorem was probably proven sort of independent of persistent homology, right? Like it was, persistent homology was getting started, but I don't know if the two communities really knew each other yet, right? But interleavings sort of were developed inside of applied topology, and now you're using them to give an extremely nice and quantitative proof of Latschev's theorem. These correspondences, I mean, where the scale changes. Yeah.
I think it's becoming very standard in persistence also. Any more questions?
Yes. Other questions for Sush? Well, if not, thanks so much. And let me stop the recording here.